record on this computer. Okay, looks like recording is on, and share my screen. Awesome. Okay, welcome everyone again. This is our second session on Introduction to PyTorch. In our first session, or in our previous session, we covered half of lesson 4, Introduction to PyTorch. There's quite a lot of content there. We weren't able to complete it. So our goal for today is to finish the remaining of lesson 4. And if you're new to this meetup, this is the meetup page, Nova Deep Learning. This is our session 3 actually in this course. We have here all the information. Braga put here all the information. She's the organizer of this course. If you missed the previous session, part 1 of 2, as I call it, it's over here on YouTube. I had an issue with the camera last time. I wasn't able to record the entire screen, so I apologize for that. And the audio quality is not as good. I switched to a different audio and a different visual system now. We're using Zoom, and the video will be uploaded right after the session. So you'll see a link here, so that you can look at it in your own time. But let's jump right through it. I know in my last session, in part 1 of lesson 4, which is over here on YouTube, I talked a little bit towards the end of these loss functions and what different functions do we use. I found a very good resource online, and I'll share it on the meetup page. But there's this a very good YouTube video from Aurelien. He used to work for YouTube on their machine learning platform, recommending videos, and he's done a very good explanation here, a very good job of explaining what is entropy and what is cross-entropy, and what does that mean with some very basic, simple examples of using, for example, a weather station. So based on your weather condition, if it's sunny most of the time or if it's rainy most of the time, how much information does the weather station need to actually send over to users? So that is a quantifiable metric. We can quantify it in terms of bits. And that's how you measure the entropy or the uncertainty when you transmit information. Then he later on talks about what is called cross-entropy. Basically, when you're trying to measure the distance between these distributions, how different are these two distributions? There's something called divergence or KL-Divergence, and that's a metric that is known as well in information theory. So both of those two topics are used in machine learning and deep learning. So feel free to watch this video and ask us any questions you want. Next time, perhaps we can take another look there. Just a quick reminder as well, all the code I'll be covering here are in this GitHub repository, which is right here. And I'm running this from Colab. Colab is basically Jupyter Notebook on your Google Drive, and if you go to our code, you'll see that I'm continuing from lesson or module number 4. So I'm going to go to the beginning. Awesome. Any questions so far regarding the last session or any clarifications before we start? You can chat or you can unmute yourself and talk. Okay. Questions. Cool. Now we'll start with module number 4. This is now using a more challenging data set. Instead of the handwritten digits that we saw last time, we're actually going to use an actual data set, which is called the Fashion MNIST. The Fashion MNIST has thousands of images, and they're 28 by 28 grayscale images. As you can see here, it's maybe kind of hard, so let me zoom in a little bit. But think of it as like pictures of fashion items like clothes, shirts, sandals, shoes. There's a different variety of all them, all sneakers, bags, anything you usually see on a typical store. Most of it are here. Let me zoom in a little bit so you can see my screen. There you go. So this is a challenging data set, and from our previous discussion, our last session, it will require a little bit of a more fine-tuning and a more structured design of our architecture. It probably will require a little bit of a deeper model, and we have to play around with different hyperparameter tuning. We have to play around with possibly in data augmentation. We'll see. So as a reminder, we're getting this data from PyTorch dataset. We don't have to import or export anything from the internet. We simply import Torch Vision for these datasets that we'll be using. Sim transforms is a module that allows us to transform our data, normalize it, shift it, basically do any kind of data augmentation features. Some plotting here, modules that we import. Then here, first thing we have to do is we have to set up this, what I call transformation steps. And that basically means that we have to convert whatever images we get to tensors. We usually do some kind of normalization so that the color is not skewed too much, too bright or too dark. We do some kind of normalization here. Then how do we actually get the data? We use this from Torch Vision import datasets that you saw here, this module here. That dataset has multiple datasets under it. One of them is the Fashion MNIST. And this is here where we specify the path. We want to download it. We want to download the training set here. Train equals to means that download the training set. And we also want to apply this transform steps that we defined earlier. Once we do that, we convert these thousands and thousands of images into smaller batches, and each batch is a collection of images of size 64. We want to shuffle them, so every time we run this code, it picks a different batch, basically, of 64 images. And this train set now passes to this transformation, and is ready for us as what is called a loader or an iterator in Python. So we can iterate over it. We can get one image at a time or one batch at a time that has 64 images. We do the same for the training set. The only difference here is that this train equals false. And we pass it to the same transformations. Similar, we group it to a batch size of 64. And we also shuffle it, so next time we run this, this is shuffled. And if you want to look at a sample training image, remember this is an iterator, so we use this iterator method in Python. We just get one item out of it, and or the next batch out of it, and then we get the first image out of that batch, and it looks like this. I saw some feedback here. Let me make sure nobody has. Okay, so there's a question here, Peter. Is there a separate train and test set, or does train equals to just mean that we want to get labels along with images? It's actually a different, yeah, it's actually a different set altogether. So let's say there's 100,000 images here. Probably 80,000 of them will be in the training set with labels. 20,000 will be here with labels as well, but so that we can do the comparison. So this is labeled. All the data is labeled. This is supervised learning. Awesome. So then we have an idea of how our data looks like. This 28 by 28 grayscale image. And there are 10 classes here. Remember, we saw like shoes, bags. There's 10 different classes. So one way we can tackle this challenge is, for sure, we're going to have to convert this 28 by 28 to one vector. Remember, we do that through that 2 tensor. And we basically convert this square representation of an image to a very long vector of 28 by 28, which is 788 pixels. And then we have labels for each of these images, and that label can belong to one of 10 classes. So this notebook here recommends that you have at least 1 or 2 hidden layers, and recommends some activation functions as well as loss functions. So this is us then defining our network architecture. We're importing a neural network and optimizer that we're going to use later. We start with what is called a sequential model. Basically, we stack different layers next to each other or on top of each other, if you prefer. So we start with a linear layer. This is basically a fully connected layer. It takes as input the 784 pixels. it downscales them, or it is connected. It outputs 128 outputs out of it. So out of 784 units or inputs that we get through this fully connected layer, that fully connected layer has only 128 units. Then we pass that through a ReLU, a rectified linear function for the nonlinear part. Then we have another layer out of those 128 outputs, and we pass them to a fully connected layer, and we only output 64 of them. We pass that to another ReLU layer, and then in the end of the day, we have these 64 outputs. Another final layer, a linear fully connected layer, that we just output only 10 numbers, and out of those 10 numbers, then we pass into this log softmax function that we're going to use later to see where we are. But these are not probabilities, and these are we can really to actually convert them to probabilities, we have to take the expectation of the log, so we can just get the actual label. So I call this model. I was playing around with naming conventions. It's kind of tricky when you do this, but in the beginning I said maybe I'll just create one model. I'll give it a meaningful name of the different input size, the first hidden layer, the second hidden layer, third layer, so I have an idea to refer to it later on. So I did that, and I'm just showing the model here. You can see that it takes as input 784, a vector of 784 pixels. It outputs 128. All of them have biases, so each layer, remember, has its own matrix of weights and its own vector of biases. It passes through another layer of ReLU, linear log softmax here. And so we define our network architecture, and this is basically how the information will flow from left to right, from input to output. Now, somehow when we get this output, these 10 values here, we need to compare them with the 10 values of the labeled images. And remember that that label will basically be all zeros, and it will have one where the true label is. So let's say if the first class is, let's say, shoes, and we happen to come across a shoe, then the true label will have a 1 for the first part and 0 for all the other parts. Our network probably will estimate, let's say in the beginning, some random values, let's say 0.1, a uniform for all of them. So we'll say 0.1, 0.1, 0.1 for all the different classes. Then what this method here will do is the negative log loss. You will compare this to distributions, and it will come up with a difference. And then we use this difference in the optimizer, and we use the stochastic gradient descent, where we take the gradient of all our layers, so that how much do we have to change our weights and biases so that our output is closer to the true label. So that happens in the loss calculation and in the backward propagation here. Cool, so we have defined these modules. We have to put them together, and we actually have to run them iteratively as we go by, so that eventually we have what is called convergence, and we have a good performance, and we try to match the true labels as much as we can. So yeah, so remember we do a forward pass to the network to get what is called the logits. These are not probabilities, these are just network outputs. We use the logits to calculate the loss. We perform a backward pass through loss backward to calculate the gradients. And we take a step with the optimizer to update the weights. Those are basically the core 4 steps that we do in a loop. You can also adjust the hidden units, the learning rate, and all that later on. So one hyperparameter here is the epochs. Epochs means how many times we're actually going to see the entire data set, the entire training data set. In this case, we're going to see it 3 times. And remember, every time we see a training data set, it's actually packed in batches of 64 images. So for each epoch here, we have a variable here that just calculates the running loss. Then for images and labels, this is the actual input, this is the actual label, a vector of 10 items. This is a vector of 28 by 28. In this train loader, which is basically contains all our training data, we flatten it. So we take the 28 by 28 and we convert it to a 784 long vector. Then we clear the gradients. This, by default, PyTorch, this is something you have to remember, always accumulates the gradient. So when you do this, you have to make sure that you make them 0. Then we have our model defined above. We pass the image, which is now a vector of 784 items. We compare the output of our model with the true label. We see how different that is, and that is defined by this criterion here that we saw above, right here. Then we take this loss and we do a backward step. But what that will do is we'll actually calculate the gradients and actually, that's it, calculate the gradients. Then using the optimizer step, that will actually take these gradients and actually update the weights based on the gradient that we saw here above. And then we just keep a track of this running loss. We just add the current loss and we plot it over time. So if we just run this network for 3 epochs, you'll see that in the beginning the loss was, or the running loss was, 1 point something, went down to half, went down to 0.4. And if I want to see how that looks like, this after 3 epochs, this is a random image, and it was able to classify it as 50% shirt, 50% t-shirt top, which I think is pretty good with just 3 epochs, considering we only run it for 3 epochs. So let's see here what we're doing. So we're actually taking our test loader here, which is the entire complete different data set that our model has never seen. We take the next batch. Remember, this is a batch, this is not an image. So this is basically 64 images. We take the first image of that batch, we resize that, because remember, our model only accepts vectors. We pass it through our model. We're going to make sure that we turn off gradients. We're doing evaluation here. There's no need to calculate any gradients. We pass it through our model. We get what we call, because we're using a log softmax output as our final layer, to actually get the probabilities, we have to take the exponent of it. So e to the power of that log softmax, whatever our model outputs. So we get our probabilities, and this is what is shown here as the x-axis, and the y-axis is the different classes here. So this was pretty cool. You can play around with this with different images here. You can see how close you are with just 3 epochs. And again, this is the model that we used. A three-layer model and a log softmax in the output that gave us this decent result. Let's dive a little bit deeper now on how many datasets are contained here. So the training part, the training dataset has 60,000 images, and the test dataset has 10,000 images, just to give you an idea of the scale. So when we do an epoch of 3, that means we go through this 60,000 images 3 times, 180,000 images overall, even though 60,000 of them are unique. Cool. I will take a pause here before we explore other architectures or different ways of doing this better. Feel free to chat in or unmute yourself and ask any questions.
Yeah, I was wondering how you decided to pick the negative log likelihood versus cross-entropy for your loss function. Does it make a difference, or are there cases where one would be better than the other?
Yeah, that's a good question. I actually plan on giving maybe a deeper discussion on this. I know this is a good question. I don't have a very good answer for you right now. Let me do a bit of research. That's my homework, and maybe we can cover that next time. But
okay, great.
I know that impacts for sure your network, and also there are loss functions that depend if your data has discrete outputs. Like in this case, we have discrete outputs, or something else. Maybe you're just trying to estimate like price number of a house, for example, if it's continuous. Right. So that depends.
Okay. And what about the finding the gradients? So you could use the stochastic gradient to center the atom they talked about.
Yep.
Do you know one's better than the other? It seems like all the examples use the SGD, but in real life, everybody seems to use the atom.
Yeah.
I don't really know what the difference is.
It is the first one, yeah. I will quickly give you the quick answer of it. There's this website called Deep Learning AI Nodes, and there's something called parameter optimization neural networks. The formulas are different for the optimization. There's a nice notebook here that I like. This one. This one, yeah. So there are different optimizers here and different learning rates and different rate decay. So let's say
nice.
we want to compare all of them, and let's say our cost function looks like something like this. So this is the initial point, and then you can see the local minimum and the local are distributed around here. So based on where the initial point is, some of them will converge faster, some will converge slower. So let's see, which is the purple one? Oh, here. Sorry, let me make this a bit smaller so we can see. So the green one is the gradient descent. The yellow one is the atom one. The orange one is the RMS with RMS prop, and the purple one is momentum. So there are differences in. Let me stop this. There are differences in their formulas, but the short answer is, if you look at this from a physics perspective and you're trying to optimize a function, some of them look at it from, okay, what's the fastest way for an object to move to a local minimum? So you can look at maybe speed. Some other ones like atom and RMS prop, they actually look at acceleration. They look at the derivative of speed to look at second moments basically, and they combine it in their formula. Some of them do some kind of smoothing or averaging. So in case your function is not that, I think there was an example here. This is a very smooth function, so you can easily find, based on derivatives, where's the local minimum, local maximum. But let's say your function was not this smooth, then you might actually, or if your learning rate was very high, you might actually end up going like left and right and never being able to achieve this minimum value. So all of them take this into consideration, how fast you're going down, if you're looking at the past, if you're looking at just the speed, or if you're looking also at the acceleration. So there is a little bit of math there, and also like for the way that I understand it from a physics perspective of how does something converge.
Okay, thanks. That was helpful.
Okay, somebody is okay. If you don't mind muting yourself, I guess we're getting some echo from somebody, and if you have to, speak up, then unmute yourself, please. Cool. Okay, I will come back to this notebook again. This is where we would explore different network architectures. But before I do that, I actually use some new concepts that are covered in this other notebook. So let me go to notebook number 5. I'm actually doing inference and validation. We did inference for only one image. We want to do it on the entire test set, so we can have an idea of our model and the entire test set. How many do we get? Do we get 50% right, 60% right? That'd be our accuracy. So why do we want to do this? Simply because just training on our training set is not enough. This is data that the model has seen before, and you can run into a problem called overfitting. So overfitting is when your model is large enough, has many layers, has many weights and biases, and can basically memorize your training data. We don't want that. We don't want the network to memorize the data. We want the network to find patterns in the data, but not explicitly memorize the concept. Think of it like when we go to school, or when kids used to go to school, or kids nowadays. You don't want them to memorize the entire, physics chapter and recite it letter by letter. You didn't really learn much if you did that. You want them to learn the concepts, like gravity, or time, or space, or derivatives, or travel. So that's what we're trying to avoid here with making sure that our model doesn't overfit. And there are multiple ways to do that, as we'll see. But for now, we're trying to find a way to make sure that we're not overfitting, and we do that by comparing our model or using our model on a complete different set that it has never seen. That's a test set. So as before, this is the exact same setup, the exact same data set, the MNIST, the Fashion MNIST. Very similar layout, a 4-layer network. We don't have any, so this is another way, if you remember, with this functional of defining the network, where you have your fully connected 1, 2, 3, 4, and then each and every one of them you pass it through this ReLU. This is another way of running our network, and then again this softmax of the final one to the final output. Then we take our next batch of test data. We take the exponent of it, because we use this log here. This log, for us to actually get the numbers, we have to use the exponent of it, so that they can negate themselves. And then we can see that what did we get as an output? So let's take it a little bit deeper here. From the output, somehow we want to pick, this is 64 examples, that's why it's 64 by 10. So we actually ran this on the entire batch. So if I look at one output, ideally we want to pick, so our network will actually give us 10 numbers, if you remember from here. We don't want 10 numbers, right? We just want the class that is the most probable, that our model thinks is the right model. So to do that, we have to pick the top one. And PyTorch has a method called top k, which basically allows you to pick the top k items out of a list. In our case, we have this list of 10 items. We want to pick the first one, or we want to pick the top one of the first one. Could be anywhere in the list. This is us specifying here that in this list, just give us the most probable item, meaning the item that our model thinks is the most probable. So that will actually give us that value, but also give us what we're interested in is the index, because the index tells us what label it is. So if we do this for 10 random images, this is the index of each one. This is basically class number 2, class number 7, and this number directly correspond to different fashion classes. So 2 could be a shoe, 7 could be a shirt, 9 could be something else, and we'll see that. Great. So now that we have the most probable, we want to compare that to the true labels. And one way to do that, if we do this equal, I'll actually compare the top class with what the label is. And here, just some note about when you do this equal and assign it to another variable, this is actually now a Boolean, so you can't really use mean and all that. You have to format it a little bit. But so this is the final expression that you want to compare your equals, which is basically if my top class is the same or not as my labels, and then you want to compare that across, let's say, an entire batch. And it's in this case only 3% of them match. You know, the accuracy is 3%. We just ran this network once. We didn't even train it, basically. So without training this network, we got 3% accuracy just by pure random. Then what we do here is when we use our network to test, we don't want to calculate any gradients. So PyTorch has this this method called noGrad, and what that means is it tells Torch in the backend to stop calculating any gradients for every image that passes through our network. So when we turn off the gradients, we iterate over the test data set, and we compare it with the actual labels. So let's see here. Again, this is an untrained network. Here we specify the epochs. We keep track of some losses here and accuracy for training and testing. And then for each epoch, which are 10, we go through the training set. We zero the gradient, we pass it through our model, we calculate the difference, we do a backward step, and we calculate the gradient, sorry, and then we do a backward step. And we keep track of the training loss. Once we're done with that, this else is an interesting concept in Python. So when you do for and else, this else will be executed when this for loop is done. So basically, this says that when you're done training, come here and actually calculate the accuracy. So in the beginning, these are some variables we'll be using. We set them up to 0. We make sure that we turn off a gradient so we don't do any unnecessary work. Then we iterate to the test data set. Again, we pass it to our model. We pass it to we compare it to our criterion to see how different they are. We pick our output of the model, the most probable one, and we compare that with the labels. And that's we store that in equals. We take the average of those equals across the entire batch, and then this is what we output. So then here, as you'll see, as the network trains, you'll see the training loss, which is the first column. You'll see the test loss when this is done. And then you'll also see the test accuracy. So as the network progresses here, you'll see the training loss going lower and lower and lower. The test loss and the test accuracy could be, ideally should be going, the loss should be going lower and the accuracy should be going higher, but then that's, that depends on our network. And then if you want to plot these columns and see how they look like over time, this is one simple graph here. We have the epochs here, and on the x-axis 1 through 10, or 0 through 9, and on the y-axis we have our training and validation loss, and on the right this is a dual axis, and on the right we have our accuracy. So the validation loss is the orange one. You see it starts pretty high, and the axis for it is on the left. Then we also have our training loss, which is here in blue, and I think accuracy is in green. It's hiding behind here, that's why it's hard to see. So speaking of overfitting, in the beginning, remember we talked about we don't want our network to memorize things or without finding patterns. So this is one classical example where you see that the validation loss, the training loss is the output of our model and data it has seen. So the loss is lower and lower. That means that the network is memorizing or learning. We don't know. Could be doing either. But when we look at the validation loss, when we compare it on data set that it has never seen, we see that the loss is actually going down and then slowly goes up. So that means that after this point here, the network basically is trying to memorize the training set. So it's doing very well on the training set, the blue part. It's doing very bad on the test set, the validation part. So there are two techniques for fighting overfitting, for getting rid of overfitting. Is one of them is early stopping, as I mentioned, as you saw me here point my mouse. That means that we train our network until the validation loss stops decreasing. So basically, it's like, think of it as like an investment. You're trying to minimize something. When you stop minimizing, when your loss start increasing, you want to stop it. You want to stop training there. And then your model basically, the weights and the biases would be whatever they are at this point in time. That's one way, early stopping. Another one is called dropout. So in our network, this is a very popular technique. There's a lot of papers written about it. I think Hinton introduced the first dropout paper. But what that basically means is that when you train your network, make sure that on each layer, some of the nodes on each layer are actually deleted, meaning you don't calculate the weights and you don't calculate the output going through that node. So what that does is you're basically training a slightly different network every time you train your data. So every time you train your data, the network is slightly different. So what that means is that you're relying entirely on a specific layer, on a specific node to capture most of the information. And what that node or layer is doing is actually memorizing. You wanna make sure that doesn't happen. So if you drop it, that means that everybody else, all the other nodes and all the other layers have to pick up the work so that they can learn they can train the network and the network can perform better. So that's the dropout. Let me drink some water. How do we define it? It's very simple. We have our linear networks here, are fully connected, 1, 2, 3, 4. And then in the end, we have a dropout of 0.2. So what that means is that So it will drop a module, in this case a node, on our network with probability, 20% probability. So 80% of the time, it will keep each one of them, and then randomly some of them will be dropped with 20% probability. And then we forward this through, we actually do this on each layer. So we have our fully connected one, we pass it through a ReLU, we pass it through a dropout. Sorry about that. But basically now, in the beginning, if you remember, we had a fully connected ReLU, fully connected ReLU. Now we have fully connected ReLU, dropout, fully connected ReLU, dropout, fully connected ReLU, dropout. For each layer, we want to make sure that we're dropping some of the nodes so the network doesn't overfit and doesn't remember exactly the training part. And the test part is exactly the same. Nothing. There's no dropout here. When you evaluate, make sure that. So when you do this model.eval, this is the comment here. You set your model to evaluation mode. That means that do not use dropout. Awesome. So then this is our network with dropout added. You have your cooking ingredients, if you remember from our last session. And this is in the forward method, is how you add them up. So you take your image, and your image is in this X. You pass it to this fully connected layer 1. You pass it through ReLU, you pass it through dropout. You take that output of the first layer and you add it to the second layer, which is another fully connected layer 2. You pass it through ReLU, you pass it through a dropout. Take the output of the second one, you pass it through the third and fully connected layer, ReLU, dropout. You take that and you pass it to the last fully connected layer, which outputs 10 numbers. Then similarly we define here, so this method, we call it classifier. We call it here, we instantiate it, we create a model. We call this method basically. We define a criterion optimizer. In this case, we use an atom with a learning rate 0.003. And now here in this case, you can do it for as many epochs as you want. I did it for just 10. We're iterating over the training set. We're making sure we zero our gradients, model, loss, backward, or gradient calculation. Use that gradient calculation to actually update the weights. So we do this 10 times. And we're done, we go through our test set, we put the numbers. And if we want to plot this, this looks much better now. So we have our validation loss in orange. So we have our training loss in blue. That's good. We want to make sure that our validation as well is also in line, is also monotonically decreasing or is not increasing significantly. And then we have our test accuracy on the green one. This is a very good graph, meaning that using dropout, we significantly boosted our performance. If you remember the previous graph, let me quickly scroll up. It wasn't quite at all like that. It was a little bit more random and chaotic. Here it has a much better structure, and you see that as you train this for more and more epochs, this will look even smoother. Cool. One more module before a question. Do you typically do dropout on every hidden layer? Yes, if the layers in this case are the same, yeah, it makes sense to do on every layer. You don't have to. I think it's a good idea, best practice to do on every layer. Good question. Cool. So now let's train this, or let's use this model now on data has never seen. So how do we do that? We make sure that our model is in evaluation mode, meaning it won't calculate any gradients. Sorry, it won't run any dropouts. As well, the no gradients part is here, but this means that do not run any dropouts in when you pass your input through this through our model. Then we take our next batch, 64 images. We just take one here, and we just put one example here. And we saw here, this is between a shirt and a pullover, and even us, I don't know if I can tell or not. It's very pixelated. We're not sure what it is. So it's pretty decent. Also a little bit of a code here. But this introduced basically dropout, which is something that we definitely want to use in our network. Any questions before we go to the next one? The next ones are pretty short, and then we're going to summarize the number 4 here pretty soon. Cool. So let's talk a little bit about number 6 here. When we do this, if you notice, we have to train our network, then test it, and then when we come back next time or tomorrow, we have to train it again and test it to see where we are. You know, if you want to roll this out as a product, as a in production, that doesn't make any sense. When you train your network, you spend so much time. You better save the state of that network and that of those weights and those biases somewhere, so that tomorrow you can pick up from where you left. So that's exactly what the saving and loading models module does. So it introduces, so it's the exact same setup. You train it. What introduces this model. So if you want to print our model to see how it looks like this. But if you actually want to see the weights, how do you do that? You do that through this model.state dictionary. So that's what this sentence is saying here. The parameters of the entire network are stored in the model's state dictionary. It contains the weights and the biases matrix for each of our layers. So this has 1, 2, 3 hidden layers. If you want to see the actual weights and biases, the state dictionary will have a name. It will be like hidden layer 0 weight, hidden layer 0 bias, hidden layer 1 weight, hidden layer 1 bias 2, and then the output. And if you actually want to see those weights, scroll up a little bit here. So this is what is called an order dictionary. It's actually, think of it as something as like basically in Python dictionaries don't have order. In this case, the order is important. So you have a key and a value. So the key is the weight, and the value is this entire matrix of appropriate dimensions. And the bias is just a vector of appropriate dimension as well. Then hidden layer 1 weight, hidden layer 1 bias, hidden layer 2 weight, hidden layer 2 bias. You see, it's very easy to get confused with the naming convention. So later on, we're actually going to name these layers, so it's easier for us to refer to them. And once I have that model, once I trained it, what I can do is I can just call torch.save. I can pass the model state dictionary, and I can give a path. In this case, I'm just giving a path in my Google Drive. I can give it a name, something meaningful. My Fashion MNIST checkpoint. That basically means store all these weights and biases into this file. And later on, when we come tomorrow, I don't have to train it from this point. I can simply do torch.load, the exact same file, so make sure you don't lose the file. And I have my state dictionary. I can look at it, and then I can call model load state dictionary. So there's this model here that takes a state dictionary. It loads the weights and biases to our model. And our model now is basically where we left it a day ago. One note here that if you save your model's weights and biases from one network, and if you try to load it in a slightly different network with different number of hidden layers, or different number or different size, it won't work. You will get an error, and it will say that you're trying to copy something of this dimension to something of this dimension. Those dimensions don't match. So make sure that your network architecture is basically, in terms of size, is exactly the same. So this is us then defining the same network as the one we saw the file was, and we save it, and we can actually create a method here, which what all it does is takes a file path, it reads that path, and then those weights and biases, then uses that to actually create a network on the fly. So here we use that checkpoint. It's labeled as input, output, hidden layers, and we do that because now when we save this state dictionary, we actually saved it as part of a larger dictionary. I skipped this. So we have now a new dictionary called checkpoint. We can here specify the input size, the output size, and the hidden layers, and the entire actually weights and biases. So we actually are saving some metadata about our model. So we store this entire object checkpoint here, and we can recover it, and we can create a new model, load from it, return the model. We call this method here, and we can see the weights, the dimensions match. So this is us storing a little bit of metadata basically for the network. Any questions in storing and loading? So saving models and recovering them from our computer? No? Cool. Continuing on. The next one actually covers a little bit of time in loading image data. You can take a look. It's something we've seen in the past, but all it focuses on is how do you structure now. So you see we're going more and more towards like a production environment where you actually store your data in a proper format. So in this case, let's say we're going to classify 2 classes. In this case, this example is just classifying dogs and cats. All it's saying is that make sure that your train and test, your entire data set, whatever you have, we'll figure out later how to split, but make sure that dogs are in separate folder, and you can have a picture for each one of them, and make sure that cats are in their own separate folder, and you have a name for each one of them. Then when you call this data loader, it will automatically recognize, like in this case, it will automatically recognize the different categories based on the name. You don't have to say that label 1 or dogs is in this folder, label 2 or cats in this folder. It will automatically detect it for you, this image folder data set. It talks a little bit about data augmentation, and I have some examples here. You can do rotation, remember, you can do crop, meaning if your network expects a specific size, which that's always the case, you want to make sure that you crop it to X by X dimension. And I have some outputs here. So this could look like the raw data, and then this is the test data, and sorry, this is actually transformed images. So this is the original images, then this is the transformed images. So it could be like close up, you see here, maybe rotated, maybe part of it zoomed in. That's how it looks like on the training and the test data. So this is basically us. Let's say we had 10,000 images and we want to get 20,000. We can simply rotate, scale, zoom in, zoom out, just to get different perspective of our images. Cool. So that's on image augmentation. And the last one is, or second to last, is this concept of, transfer learning. So remember our network, we trained it, we're able to store our weights and biases in a consistent format. We're able to retrieve them, and we're able to do inference. Let's say we have a very complicated task, like, okay, dogs and cats probably can do a decent job. For the fashion MNIST, the data, as you saw, it's very well structured. It's something on a black background. That we had pretty decent performance, like 85% accuracy with a fully connected layer. We were trying to do cats and dogs where we have now 3 channels. We have green, blue, and red, and also the size is bigger. That fully connected layer is not enough. Not only that, but fully connected layer does not perform very well with images. Images have spatial information in them. So, there are objects, and when you look at an image, the tail of the cat is part of the cat. It's not, separate. So that spatial information, when we convert our image to a vector, is somehow there, but it's not really easy for the network to pick out. So that's why in the next course, in the next one, which is here, lesson 5, it's a completely new architecture, convolutional neural networks, where actually are able to extract that spatial information from images much better than in fully connected layers. So, well, let's say we haven't learned about convolutional neural networks yet. All we heard is, hey, there's this new, or there's this cool network architecture, and it's called XYZ. It performs really well on images. Okay, can we use it? Like, PyTorch gives you that flexibility, and that's called transfer learning. So transfer learning is taking a model, you can load it on your computer, you can use it as it is, or you can take the final output, you can remove whatever classifier the original network was doing. Let's say it was classifying 1,000 images or 1,000 classes. You can convert it to 10 classes. You want to just classify 10 classes. And you can just train the last part of that model, given that the entire model is probably a gigantic model of millions or even billions of parameters. So this model introduces this torch vision models. And we'll use this on our cats and dogs data, which are 224 by 224 and also 3 channels. And here we actually normalize the channels. So something that's very blue, we try and normalize it. Something that's very blue on one part of the image, we try and normalize it across the entire image. So we do these transformations, we get this data. Cool, how do we get our new model? We haven't defined any model yet, right? So remember we imported from Torch Vision import models. Now that models, if you see, has many predefined architectures that PyTorch maintains. And in this case, we're using something called DenseNet 121. If you click on that link in the documentation, it will take you here. This is a model from densely connected neural networks. And actually, it's a paper from 2018. So this paper explains how the densely connected neural networks work. You don't have to know all that. All you have to know is what is called dense one-to-one. So you can read it. You can say pre-train true, meaning, yes, please give me, whenever you train it, give me the weights that you train it on a given set, on a given data set. You see it's a very complicated and a complex model. It has many layers. It has convolutional layers, batch normalization layers, ReLU, max pooling, has something called dense block as well. Has many different parts that we haven't seen yet. And it's probably very long. It's probably 121 layers long. Usually these layers take their names, these models take their names from how many layers they have. And at the end of the day, you can see here that it outputs 1,000 classes. So this was, it takes 124 inputs and it outputs 1,000 classes. So this was probably trained, I think, on the, let's make sure, on the ImageNet, yep. So it was trained on 1 million labeled images in 1,000 categories. And there's a link here where you can learn more about it. But I think it's everyday objects that you see, you know, like cars, airplanes, animals, humans. Like there's a lot of 1,000 categories that it was trained on. Cool. So we can take that model now. And remember, I told you in the end that this has 1,000 outputs. So let's see, I think here we are. So model parameters. Yeah, so we're doing here, we're taking those, actually, no. We're taking the last layer of this model, which was 124 by 1,000. We're taking that. It's called classifier. We're replacing it with our own classifier. So we're taking that. We're defining our own layer, which takes us 124 from the last layer of the train model, converts it to a 500 output, applies a ReLU. From 500 output, we go to 2. We only need 2 outputs. This is a dog or a cat. And we have a log softmax in the end as well. And then we say model.classifier, the original classifier from the model, which gave 1,000 categories, is now our classifier, this classifier. And this classifier only gives 2 outputs. So that's pretty cool. We basically took a really complicated model. We just took the last layer, we had our own layer, and now we can use it as it is, so we can do some fine tuning just for the last part. The last part still needs to figure out how to go from this 124 features that this network calculated, how to go to this 2 outputs. So to do that, this notebook is saying that you actually need GPU. So when you run this on Jupyter on Colab, sorry, if you go under runtime, change runtime type, make sure that you have selected GPU here. By default, it's CPU. None is CPU. G is graphical processing unit, GPU, and T is TPU, tensor processing unit. This is a platform that Google maintains and has released that performs in many cases better than GPUs. So Torch has methods of moving data from CPU to GPU. This is where you get a little bit into the hardware part of training your model. This model, if you want to fine tune even just the last one, it's much faster to do that on a GPU. So this is to give you an idea of a comparison. This is us looking at CPU and GPU or CUDA. We're doing the same optimizer here. We're just doing one backward propagation, I think, one pass, one backward propagation. Or actually, we're doing entire training here. Yeah, we're going through the entire training set, and then we're giving some outputs per batch on how long did it take. So if we do training of this network on CPU, it takes about 2 seconds per batch, which is 64 images. If we do it on a GPU, it takes about 0.01 seconds. You know, it's like magnitude of order faster. So then we do this check here. If CUDA is available, then we use CUDA. Otherwise, we'll use CPU. We take our model. We have our classifier. We train. So we train only the classifier parameters. So here, when you do the optimizer, you can specify exactly what you want to train. By default, we give the entire model. Here, we're giving the model classifier parameters, meaning don't change the millions or billions of parameters of the original dense 121 model. Only change, you know, the however few thousand parameters that you have here. Cool. So we do that for 3 epochs. This is basically fine-tuning that last layer. We do forward, backward pass, and then we see that our accuracy is increasing, you know, significantly. We can try, the good thing about this, we can try another network. We can try ResNet 50. It's a completely different architecture. We can do that as well, 95%. We can do that with something else called VGG16. Let's see, 91%, you know. So in the high 90s, all of them perform very well. Cool. A few more questions before we wrap up where we left here in exploring different network architectures. Make sure in our chat. Okay. So in my note, this is not in the notebook, but I added this. I spent some time. There's a little bit of Googling I had to do, but basically what I wanted to do is, okay, I can create different network models, different network architectures. It would be nice to see, this is where we get into the hyperparameter tuning. It would be nice to see how depth affects performance, you know, how height or size of the network, you know, how large is this hidden layer affects the network. What if you have different, like Peter, you asked, what if you have different activation functions, or what if you have different optimization function or loss functions? Like, how do these all things play into effect? So this is me trying to put like almost like an easy function for me that I could just give inputs. Okay, I want this many hidden layers. This is my input size, my output size. I want this many hidden layers, and I want this specific progression. I want a specific activation function, and I want a specific loss function. And this method here basically does all that for me. It took me a little bit of time, but the trickier part was how do you actually add modules or add layers? It's because I wanted to add layers dynamically. If I want to say 5 layers or 10 layers or 20 layers, I wanted to do that. Then if I wanted different optimizers, if I wanted a negative log loss or stochastic gradient or atom or RMS prop or whatever you can add it here. And also wanted to incorporate the test part and picking the top one, and also some kind of printing here. So this is a long one. Feel free to take a look. But basically, what it looks like is I want to create a model of 784 input by 10 output, 3 hidden layers, 128 is the first one, ReLU, log softmax. Cool. How does it do? This is how it does. It gets 85%. This is fully connected, okay? Cool. Let's see if I make this and how it looks on just one example. Pretty decent. It gets signaled pretty good. How does it do the entire test data set? You got right 8,500 out of 10,000 units. So I did 85% right. Okay, if I want to see, did it have any preference? Where did it better in terms of the 10 categories? You see, you got 85% of the t-shirt and right. The t-trouser were a little bit easier to get. Coats, for some reason, it didn't do well. Shirt, you think it do easy, better, but think about it. Maybe shirt is kind of overlapping with other classes. I'm not sure. That's why it got a bit of a low performance here. Sneakers were easy. Bags, pretty good. 94% accuracy. Ankle boots, 98%. So maybe they're easier to distinguish. Cool. So now I want to use the same method. I want to create a completely different architecture with, if I don't specify the input size or any of them, they have a default size. But I want to change the loss function and the optimizer. Okay, how it looks like. 84%, you know. Just some random images on the entire data set, 84%. Okay. Now, if I want to add 5 hidden layers instead of 3, how does that look like? So this is a deeper network, basically. Actually, I think it would do better, but look at this. You got 71% here. And so maybe my choice of hyperparameters, you know, affected this. But as you can see, consistently bags and these ankle boots that are consistently outperforming. Okay, now let's do 5 hidden layers, but change the learning rate and increase maybe the epochs. Okay, that I would imagine will do better, 85% again. But we see that we peak at that 85%. We're not able to go any higher than that. And again. Okay, so now let me go back to 3 hidden layers, but increase the size of it, increase the hidden size from 128 to 256. Okay, that got me again 85, but a little bit smoother. Like this is the smoothest graph that we've seen so far. So it looks like depth wasn't as an important part here as it was the size of it, you know, the height of each hidden layer. So 85%, I haven't seen anything higher than that so far. And that was the dynamic, what I call model creation and model validation. So that if I wanted to try different hyperparameters, I could do that with just changing the parameters here instead of me doing setting the hyperparameters, training it, testing it. I just wanted to call a function. And then here, this is just some parts that the model had on its own. I didn't really use them. Cool. I will stop here. I know we covered a lot. Any questions, feedback, clarification so far? Feel free to unmute yourself. Okay, I will. Okay, so then, as a reminder, this is the meetup page. Probably I will be posting the next one. If you want to volunteer for hosting one of the sessions, you know, please go forward. Please check out this YouTube video that I'll be posting on the meetup. This is our code. You'll see the different notebooks that we work at, on the paper. I just have a plugin for actually starting my own meetup. My first session is tomorrow. It's called Deep Learning Adventures. And if you're interested, come and join us. The first event is tomorrow at 7:30 p.m. We'll be covering deep learning from the very beginning, but instead of PyTorch, we'll be using TensorFlow. That's because we are taking this specialization from Coursera called TensorFlow in Practice. So if you want to join us, so there's a lot of people joining us already. You know, RSVP here. We have our own Slack channel. We have a GitHub repository, and we'll be pretty active. I'll make sure I'll share some of these resources as well. So I'll stop sharing here. I'll stop the recording. And